Hello everyone, welcome to our third unit of AP Physics C, Electricity and Magnetism. This one is talking about current and resistance, and then circuits, direct current circuits, which is the main type of circuits we look at. And we also talk a little bit about RC circuits at the end of the unit as well. So without further ado, let's get into the content review. After the content review, I have 8 problems, practice problems for you, so just to practice our skills. So first of all, what is current? We've talked about charge before. We've talked about stationary objects that have charge. Now we're going to be talking about the motion of charges. And that is exactly what current is. It's charge that moves over time. And so the formula for it is the current is equal to the change in charge over the change in time. But since we're in a calculus-based class, it's equal to the derivative of charge with respect to time. So it's dq over dt. And think of it as like if you have a wire, you have some amount of charge going through that wire. And so there's actually another form for this equation. So let's try to work it out. So the charge of an electron, which is what's moving to cause the current, is E. And so we can have that. And we need to know how many electrons there are. So that's going to be the number of electrons times E. Here, Ne is called the carrier charge density. So the density of the electrons. But since it's the density, we also need to multiply by the cross-sectional area to get the total volume, or like the total amount of charges that are there. So we have to multiply by area. And that's exactly how many charges there are in a certain cross-section of the wire. But they're also moving. And so you need to multiply that by the velocity of the charges to get the actual formula for current. And usually it's written with the velocity here. Now this is not any velocity. It's called the drift velocity specifically. And so it's equal to Vd, which is drift velocity. So that's just like the random movement of electrons that just moves it forward. That's what causes the current. And so this is, abbreviated as the Nevada equation because it looks a lot like the word Nevada. And so, yeah, this is another form that is on the equation sheet, but you're rarely going to use it. There's also another important concept here called current density, which is current per area. And so if you just divide by area in this, you're going to get the current density J is equal to NEVD, or it's also equal to I over area. Current density is a vector. Its direction is perpendicular to the surface element of the area, d area. So if it was like a curved surface, then it would be perpendicular to that surface. All right, so that's what current is. Moving on to resistance, the second big thing in the unit. Resistance is like a wire or a conductor's ability to, resist like current going through it. And so there's a few important key terms to know. One is resistivity, which is denoted by a rho. Resistivity is of a material, not of like a specific wire. It's of a material in general, like copper or aluminum. And the equation for this is 1 over sigma. In this case, sigma is the conductivity of the material. So the resistivity and the conductivity are inversely related to each other. Another formula for it is the electric field over the current density. So that's why we were talking about current density before. When you divide those two, you get the resistivity of a material. Now, what can you do with that? Well, you can rearrange it. You're going to get the electric field due to a conductor is its resistivity times the current density through it. That's all resistivity, but there's a different concept called resistance, and resistance is of a certain wire or conductor, not of a material. And so it does depend what material it is, and so that's why rho, the resistivity of the material, is part of the equation. But you also need to know the length of the wire and the area, the cross-sectional area of the wire. The longer the wire, the more resistance it has, which makes sense. It's just longer for a current to travel through, and so it requires more resistance. Or it has more resistance for that. And cross-sectional area, well, it's just a bigger area that charges can flow through, and so it decreases the resistance when you have a bigger area. So yeah, that's your formula for resistance, which you should definitely know. It is on the equation sheet, but still important to know. Speaking of formulas, let's move on to Ohm's law, one of the most important formulas in electricity and magnetism, specifically in this unit in circuits. Ohm's law is a relationship between resistance, voltage, and current. And voltage, if you didn't know, is just another word for electric potential. When you have a battery or some other power source, it has a voltage. We prefer voltage over electric potential when we're talking about circuits, because I don't even know why. I think it's just because V is the symbol, or it could be vice versa. But voltage is what we use, and we'll get more into that in the second part of this unit, which is circuits. But for now, we represent voltage with a V, just like we did electric potential. And so the what Ohm's law says is the voltage is equal to the current over resistance. Or, is equal to current times resistance. Because the more common form of it is R is equal to V over I. Because since resistance of a wire doesn't change, it's nice to keep that as a constant. And so you say that the ratio of voltage and current is constant, basically. Now, you call a device ohmic if it follows Ohm's law. Some devices don't because of resistance and just edge effects, some physical processes, friction, things like that. But most devices and most problems you'll encounter are ohmic, which means Ohm's law applies, and you can use this to calculate whatever you need to. Okay, similar to Ohm's law, which a lot of people get confused with, is the equation for electrical power. Electrical power is P, and that's equal to the current times the voltage. Not voltage divided by current, but voltage times current. And the reason why is if you multiply it out, you're going to get the same units, watts. It's still measured in watts. And this is just the rate of electrical energy transfer. So that's nice. We use this power equation, and yeah, that's basically it on power. And that was the first part of the unit. The second part, which is its own chapter in the textbook, is about circuits. And so this is where we get into the fun stuff like EMFs. An EMF is an electromotive force, but it's not really a force. It is represented by this epsilon symbol, and it's basically just a change, rate of change of work with respect to charge. It's dW over dQ. Although no one really uses that form, EMF is just thought to mean another way of voltage. Because an EMF does work on a charge to maintain a potential difference. That is the definition of an EMF device. And so it basically provides a voltage for a circuit. And that's how we'll be using it. There's two types, ideal and real. Ideal EMFs don't have any internal resistance. They don't really exist. We use real EMFs in the real world, but in problems it's mostly going to be an ideal EMF unless it specifies otherwise. A real EMF device has internal resistance, and so it's usually marked in a little box surrounding the EMF device and the little resistance. And I'll get to the notation of a circuit in a bit later, but it has its own resistance of its own, and so the true EMF or the real EMF of that device then would be EMF minus the small I, which is the current that goes through the internal resistance, times the small r, which is the resistance of that small internal resistance. We usually use capital R for resistance, but to note that it's the internal one, we use little r. Okay. I'm going to skip around a little bit because in the textbook, the next topic is Kirchhoff's laws, but I want to talk about resistors and in circuits before I talk about Kirchhoff's laws, because that'll make the solving of circuits a little bit easier. So resistors. Resistor is basically like a device that has a certain amount of known resistance. And so they can be placed in series or parallel in a circuit, just like capacitors last unit. This unit we have resistors. So I'm going to quickly review circuit sketching. So how would you draw a circuit? So the power source is usually denoted with either 2 lines or 4 lines. It doesn't really matter which. I'm just going to draw 2 lines because it's easier. The longer line is a positive and the shorter line is a negative. And so that's your power source, EMF device, whatever you want to call it. For a resistor, you draw like a squiggly line with like 3 or 4 little zigzags. That's your resistor, and it has a resistance of R, or R1, how many resistors there are. For capacitors, it's going to be just 2 parallel lines, just like with power source, but this time they have to be the same length. Otherwise, it would be mistaken as a power source. This is a capacitor with capacitance C. And those are the main ones you're going to want to look out for. There's also switches, which you have like three different little dots that indicate where the switch is. So this is when it's open, and when it's closed, it looks like that. And so that's a switch. Not really that important, but some questions do ask for it. So yeah, interlude over. Let's talk about resistors in series and parallel. So when resistors are in series, the same current goes through all of them. And so what you can do with that information is that if you have multiple different resistors in series, you since it's the same current, the voltage adds up. So remember when we were talking about capacitors, when they were in parallel, the same charge, when they were in parallel, the voltages were the same. So when they were in series, though, the voltages added up. So it's very similar here. The voltages add up when you're in series, and when you're in parallel, which basically means you have two different paths to choose from, or more, the voltages are going to be the same. And so what does that mean for our formula? That means that the equivalent resistance in series is just the sum of all the resistors. In parallel, the equivalent resistor, the reciprocal of it is equal to 1 over R1 plus 1 over R2 plus dot dot dot. So for capacitors, it was the opposite. When it was in series, you use this formula, the reciprocal formula. When it's in parallel, you just add them up. And so it's going to be a little bit difficult to remember that, but you do have it. I think you have it on your equation sheet. Yes, you do. And so you can remember that way, but I would suggest kind of knowing it and knowing why that works so that you don't get lost. So that's how you add up resistors, or you find an equivalent resistance. Now we can talk about Kirchhoff's laws. So Kirchhoff has two laws that can be used to analyze a circuit. Let's look at this basic circuit, getting rid of the switch, and let's replace that capacitor with another resistant. So this is R1, this is R2. So what Kirchhoff's law says is, he has two of them. One of them is called the junction rule, or the law for currents. And that's basically saying that the sum of currents entering any junction must be equal to the sum of currents leaving that junction. So if you had something like this, I don't know what I'm doing here, but let's say this is a specific junction in a circuit. If current enters this way and leaves these two ways, that means, let's call this I1, I2, I3. That means that I1 is equal to I2 plus I3. That's what Kirchhoff's junction rule says. Now, what's interesting is that if you flip the sign of this current, now there's two entering and one exiting. And so now I1 plus I2 is equal to I3. So you can change like exactly which currents are entering and leaving, and that'll have a big difference on what the equation for the current is. Then we got the loop rule, which is about voltages, not currents. It says that the sum of the changes in potential encountered in a complete traversal of any loop in a circuit must be 0. In other words, if you start at any point in a circuit, go a complete loop, the net voltage, or the sum of the voltage drops and gains, would be equal to 0. So if we use this example here, let's just start here. First, let's start down here actually, and go clockwise. So first you encounter battery. That's going to be voltage gain. Since you're going from negative to positive, you're going the right way around, that's going to be voltage gain. So you're adding some amount of voltage. Then you go through this resistor. You're also going the right way because current, conventional current goes from the positive end to the negative end. That's how Ben Franklin wrote it. But we know that electrons go from the negative end to the positive end. It's just true current goes this way, but we say that current goes from positive to negative because it just makes the calculations a bit easier. It works just as well if you say negative to positive, but Ben Franklin said positive to negative, and so we've been using it that way ever since. Anyway, back to this. So we know that the conventional current goes from positive side, and so the current goes through the resistor the same way we are going on our loop, and so we're going through the resistor the right way. That means it's a voltage drop. So this is a voltage gain, that's a voltage drop. Again, same with this, we're going through it the right way because conventional current goes this way, and so that's another voltage drop. And then there's just wire here that does nothing. The resistance in the wires is negligible. So we had 1 voltage gain and 2 voltage drops, and if you add up the specific values that you get, it should be equal to 0. That's what Kirchhoff's loop rule says. Yeah, and if you go the other way, let's say you start this way and go the opposite way, now you're going against the current, and so going through a resistor would actually be a voltage gain. It would be a voltage gain if you're going through a resistor opposite the direction of current. And if you go through a power source from the positive side to the negative side, that would be a voltage drop. And so it's important to know which way you're going, because that'll influence whether it's a voltage gain or drop. But it should still all be equal to 0 in the end. All right, so we're on to our last topic for the content review, which is RC circuits. Now, I like RC circuits because there's a lot of derivations in them, which is a reason you might not like it. But if you memorize the formulas, you don't have to derive them. But I would suggest knowing the derivation because it's an interesting process. You need to use a bunch of calculus and differential equations, and this is a calculus-based course, so it should be reasonable to expect that. I'm not going to go through the derivation here because that'll take quite a while, and we don't have the time for that. But I would suggest looking at some derivation online that would help you understand it. But briefly, an RC circuit has a resistor and a capacitor. So if this is our circuit, we have a resistor and a capacitor, and there's a time constant called tau that is equal to R times C, the resistance of the resistor times the capacitance of the capacitor. And so that is important value because the formulas that we need to know depend on that. What's interesting about an RC circuit is that some of the charge that goes through the resistor gets stuck on the capacitor after a while. And so over time, the charge would be decreasing because you're charging the capacitor and you're taking charge away from the circuit as well. Similarly, the current would also be decreasing. And so the formula for this is, let me find somewhere to write it. Let's get that. Okay, the formula is that the charge over time is equal to C times the EMF times 1 minus e to the power of negative t over tau, which I'm going to write as RC here because t and tau look very similar to each other. So that's the formula for charge. Similarly, we have a formula for the current. I of t is equal to, this is the derivative of the formula for charge, and so it's just going to be equal to EMF over the resistance times e to the power of negative t over RC. So yeah, that is, you can actually get rid of these parentheses. They don't have any mathematical value. And just moving these over here, that's our formula for the current over time. You can also write formulas for when the capacitor is discharging. Basically, when you disconnect the power source and just connect it like this and get rid of this part, then the capacitor acts like a power source and discharges some of the charge. And so the charge would be increasing, the current would be increasing, and so on. But I won't get into that. This is the basic formulas you should know for an RC circuit. And that's it for our content review. Moving on to our questions. We have 8 practice questions that I will go through pretty quickly though. For this first one, 5 amp current runs through a 12 gauge copper wire with a diameter. Copper has 8.5 times 10 to the 28 free electrons. Okay, so this is that formula I told you about, which is the current is equal to NEVDA, the Nevada formula. We know N is 8.5 times 10 to the power of 28. That is that. And then we know E is the charge of an electron, which you should know because it's on the equation sheet. You can just plug that in. It says drift velocity. We don't know the drift velocity. That's what we're trying to figure out. And area is, we have the diameter, and so it's just pi times the diameter over 2 squared. And we know the current is 5 amps. And so you plug it into the formula, you get VD, since we're solving for that, is the current over NEA. And so you plug in 5, you plug in 8.5 times 10 to the 28. E is 1.6 times 10 to the negative 19. A is, if you calculate it, you're going to get, well, it's just plugging it into this. And so you're going to get a total drift velocity of, let's see. Oh, wait, it might not, so no, sorry. We're not solving for the drift velocity just yet. That is part C. Instead, we're looking at just current, because current is, well, similar to current. Current is charge over time, and here we have current is equal to charge, charge is equal to current times time to solve for the charge. That's what we're looking for. This is each second, so it's just 5 amps times 1 second, so it's 5 coulombs. 5 coulombs is the charge, and we want to find the number of electrons, and so you just divide this by the charge of an electron, which is 1.6 times 10 to the negative 19 coulombs, and so you do 5 divided by that, and you're going to get 3.12 times 10 to the power of 19 electrons for part A. Oops. For part B, what is the current density? So that's just I over area. We know the area using this formula. I is 5, and so you divide them and you get 1.51 times 10 to the power of 6. And the unit is amps per meter squared. Interesting unit. Part C, this is what I was talking about where you're finding the drift velocity. So that is current, which is 5 amps, divided by N, 8.5 times 10 to the 28. E is 1.6 times 10 to the negative 19. And A you can calculate from there. And you're going to get approximately 1.11 times 10 to the negative 4 meters per second as your drift velocity. D, if you were to use a wire of twice the diameter which of the above answers would change? Okay, how many electrons pass through the light bulb each second? Nope, that only depends on current and time and the charge of an electron. So that would stay the same. For current density, that would change because it requires area. Area is in the denominator of current density, and so when you increase the diameter, you're increasing the area, which would decrease the current density. As for drift velocity, area is once again in the denominator, so it would also decrease the drift velocity. And so your answer for part D is it would remain the same for A, decrease for B, and decrease for C. All right. Question number 2. We've got a very similar format where we got a 14 gauge copper wire of a given diameter and given current. We're given a length, and so we can use, we're asking for the potential difference. All right, so what formulas do we know relate to the potential difference? Well, first of all, we have the current and we have the potential difference, or we're looking for the potential difference. So if we can find the resistance in some way, we can use Ohm's law. How do we find the resistance? Well, we have a diameter, which gives us an area, we have a length, and we have the material, which means we can use the formula R is equal to rho L over A. A rho of copper. So it doesn't give it to us, and it doesn't expect you to memorize it. On the test, it would give it to you, but this is from a textbook, so it expects you to go back in the textbook and look for where they give you the constants. It's approximately 1.72 times 10 to the negative 8, and the unit is ohms times meters. And length we know is, 1.72 times 10 to the negative 8. Length, it says, is 2 meters, which is pretty long for a wire. And this is 1.628 millimeters. That's the diameter. You can use it to find the area using the formula pi times d over 2 squared. Once again, so you plug it in. You're going to get a resistance of 1.65 times 10 to the negative 2 ohms. And now you use Ohm's law. V is equal to I times R. And so I, we know, is 12.5 milliamps. You have to convert back to amps. So divide by 1,000. And that is this value that we just got. And so you multiply both of them. You're going to get a voltage of 2.06 times 10 to the negative 4 volts as your voltage. B, what about the potential difference in part A? B, if the wire was silver instead of copper, but everything else was the same, that would just change rho. So let's see what the rho value for silver is. It's 1.47 times 10 to the negative 8. So it's a little bit smaller, which means resistance would decrease a little bit. And if resistance decreases, that means voltage would decrease as well. And so we know voltage would decrease, but it's asking for the exact value, not like if it would increase or decrease. And so we have to calculate it again. This time, instead of 1.72, we're using 1.48. Where is it? Oh, yeah, silver is 1.47, sorry. And then once you get that resistance, you just plug it in, multiply by 12.5 milliamps. You're going to get a voltage of 1.76 times 10 to the negative 4 volts, which, like we expected, is just a little bit smaller than the copper. All right, 2 problems done, 6 more to go. This question is a resistor with length L, area A, uniform resistivity rho, that is carrying a current with uniform current density J. So this is not giving us any numbers. We just have to use equations and formulas to manipulate variables. And so we know that, okay, this says use equation 25.18 to find electrical power dissipated per unit volume. We don't have that equation right now, but what it says is that the power per unit volume is given by lowercase p. It's equal to power, uppercase P, divided by volume, and volume is just the length times the cross-sectional area. Because if you think about any shape, the cross-sectional area and just multiplied by the length, you're going to get the volume of that shape, which is pretty neat. Okay, so what is power? Power is IV. We know that from the equation for electrical power. All right, it's asking it gives us J though, not I, and we know that I over A is J, which means this is equal to JV over L, which is good to know. It wants P in terms of E and J, so we need to somehow get V over L into E. Well, we do know that V is equal to E times D, electric field times the distance, from our equation sheet. And in this case, D and length are very similar because we're talking about a wire and going across that wire. And so in this case, D is L. The length of the wire is the distance you travel. And so that means that the electric field is equal to V over D or V over L. Well, V over L is the exact expression we have here, which means that the power per unit volume is equal to J times E as your answer. All right, that's for part A. For part B, it says in terms of J and rho. Well, we know that R is equal to rho L over A, which means that rho, which means that we can use the other form of power. Instead of IV, we can use power is equal to IR squared. So I only mentioned IV in the content review. So now would be a good time to point out that's not the only form. So you can plug in Ohm's law. So V is equal to IR into this for V. And so you get P is equal to I times R. So it's equal to I squared R. Similarly, we have power is equal to IV. And this time you plug in I is equal to V over R. And so you plug that in, V over R times V is V squared over R. Okay, so those are two more forms of Ohm's law that you should know. And I misread. It's not IR squared, it's I squared R. So the I squared R over LA. And we know that I over A is J. So it's J times I R over L. We know, let's see. We know R is equal to rho L over A. And so if you plug in rho L over A up here instead of R, the L's cancel and we're left with J times I over A times rho. Well, I over A is just J, so it's equal to J squared times rho. So that's another form for power. This is power per unit volume, sorry. And then finally, in terms of E and rho, well, we can do something very similar. In this case, it's instead of I squared R, we do V squared over R. So it becomes power per unit volume is V squared over R LA. And we know that V over L is electric field. And so this becomes E. We still have an extra V left over in the numerator over RA. And again, we can use R is equal to rho L over A. A's cancel. And we're left with E V over rho L. Well, V over L is another E. So it becomes E squared over rho as our answer. So yeah, this is actually similar to the power formula because we originally had IV, which is equivalent to JE. Well, not equivalent as in, like, they mean the same thing or they come up with the same result, but it's like you replace one variable for another. And we also have I squared R, which is J squared rho. We have V squared over R, which is E squared over rho. So it's like the same format for the different formulas. So yeah, that was that. Moving on to 25.28, which is about EMFs and circuits. So the voltage of the battery is 24 volts, but the real voltage is 21.2 volts. And so we need to find out what the internal resistance of the battery and the resistance R of the circuit is. So we know that the true EMF is equal to the EMF ideal minus I times R. Okay, so what that means is that we can replace this with the voltage symbol. And so we have epsilon I, the ideal IMF, is 24 volts, minus the current we know is 4 amps, times the resistance is equal to the real one, which is 21.2 volts. And so subtracting 24 volts from both sides, we get negative 2.8 volts is equal to negative 4R. Dividing by negative 4 on both sides, we're going to get R is equal to 0.7 ohms. So that's our answer for the internal resistance. For the resistance R of the circuit resistor, well, we know that when you add this resistor and the internal resistance, that should be the total resistance of the circuit, because also these are in series, and so we know we add resistors in series. So R plus small r, which is 0.7, is the total resistance, and we know V is equal to IR. So 24, the total voltage, including the internal resistance, is equal to I, which is 4, times this, which means R plus 0.7 is equal to 24 over 4, which is 6. So R is 5.3 volts. Sorry, ohms, wrong unit. And that should be our answer. All right. Moving on to question 5. This looks a bit ugly, but it's just an example of resistors in series and parallel. So we have a bunch of these resistors, and we know this ammeter reads 1.25 amps. So what does the voltmeter read? Okay, so there's a few ways we can tackle this, but in series, the current is the same through resistors. The voltage is different. You add up the voltages to get the total voltage. In parallel, you add up the currents to get the total current, but the voltages are the same. So let's see how we can use that. We can find the potential across this resistance, the voltage, is equal to IR. We know I is 1.25 amps, and we know the resistor is 25 ohms as the resistance. Multiplying those together, we get 31.25 volts as the voltage. And we know that's the same voltage in these two branches as well. And so we can find the current through those branches, which is V equals IR, and so I is equal to V over R. So that's 31.25 volts over, this is 15 ohms. Both of these are 15 ohms. And so when you divide it, you get 2.083 approximately amps as the current through them. And so you add up those two. So you have two of them as 2.083 and one that is 1.25 amps. And so the total current is going to be the sum of all that, because we know we add currents in parallel, and that's going to be 4.58 amps approximately. Sorry. I missed something. It still is going to be 4.58, but that's because this is not 15. It's actually, it's 25, because there's this 10 in series along with this 15. And so we know that resistors in series add up, and so we can just combine these into one 25 ohm resistor. So while the middle branch does have 2.083 amps as the current, this bottom branch has 1.25 amps because it's 25 ohms, which is the same as up here. And so that means that we have 1.25 plus 2.083 in the middle plus another 1.25 in the bottom, which is a total of, again, 4.58 amps as the total current through this little segment here. Now, since this, if you replace that with a single resistor, that is in series with this, which is in series with that, which means all those currents have to be the same. So the current going through this 45 ohm resistor is also 4.58 amps. And we know I times R is the voltage. So resistor is 45 ohms. And so you multiply those to get the voltage, which turns out to be 206 volts. And so the voltmeter will read that as 206 volts. And then B, what is the EMF of the battery? Well, for that, we need to find the equivalent resistance of the circuit. Up here, we have 25 ohms, 15 ohms, and 25 ohms in parallel. So we know it's 1 over 25 plus 1 over 15 plus 1 over 25, and you do 1 over all of that. And that's going to be 6.82 ohms. Then you add that to this 45 ohms here and this 35 ohms down here. And so you're going to get a total equivalent resistance of 86.82 ohms. Now we know that V equals IR. The total current we said was 4.58 amps. And the total resistance was 86.82 ohms. And so you multiply those together, and you're going to get a total voltage or EMF of 398 volts. So that's our answer. Not too bad. Moving on to number 6. We're almost done here. This next one is also a resistors in series and parallel question. This one looks a little bit different though, especially with this little triangular portion here. And this is one of like the tricky kind of questions that they can ask you. So we know the resistors are all the same, which makes it a little bit easier. And we know the EMF is 9 volts. Find the current in each bulb. So what can we do there? First of all, let's see if these are in series or parallel. Ignoring R1, because that's definitely in series with the rest of this little component here. Then it branches off into here, here, and here. Which then combine to form this, which is a little bit annoying. But you can actually treat this, even though it looks a bit weird, as just a complete parallel circuit. That's the trick question with this. It looks complicated, but it's just a simple parallel circuit. And the reason why is because even though these two combine to get a current here, the current doesn't go back up to R2. It just keeps on going. And so it actually looks weird, but it's perfectly normal. It's just 3 resistors in parallel. And so the equivalent resistance, 1 over the equivalent resistance, is 1 over R2 plus 1 over R3 plus 1 over R4. So that's just equal to 3 over 4.5, because all of these are 4.5, which is, and then you reciprocate that. So that means R equivalent is going to be 1.5 ohms. And you add that, because this is in series with R1, to the 4.5 up there. And so that's equal to 6 ohms as the total resistance. Now we want to use Ohm's law to find the current going through each bulb. And so we know V is equal to IR, which means I is equal to V over R. Voltage we know is the EMF of 9 volts. And resistance is the total resistance of 6 ohms. And so I is 9 over 6, or 1.5 amps. So that means through R1, it would just be the total current, because in series they have the same current. So I1 is equal to 1.5 amps. For 2, 3, and 4, though, they're in parallel, and so this 1.5 amps is going to be split among them. Now, this is easier because they have the same resistance, and so they're going to get the same amount of current each. If they were different resistors, or they had different resistances, we would use Ohm's law for each one. I'll show you an example of how to do one of them. For example, if we knew that 1.5 amps came into here, and this was 4.5 ohms, we know that the voltage would be the same. And so the voltage, we would find the voltage drop due to R1. So that would be V is equal to IR. So I is 1.5 times 4.5. And that gives you 6.75 volts, which is actually one of the questions in part B, which is, or no, sorry, not part B. Part B is power. We're not there yet, but this is the voltage due to bulb 1, or resistor 1, which means that how much voltage is left for the rest? It's 9 volts minus that, which is equal to 2.25 volts. And that is going to be the same voltage for each of these 3 branches, because voltage is the same in parallel. And so we know V equals IR. So I is equal to V over R, which is 2.25 volts over R of 4.5 ohms, which means I has to be equal to 0.5 amps. That's I2. And you do the same thing for the others, and you get 0.5 amps for both of those as well. Now for the power, you do I times V, and we know all the voltages. We just calculated them. So this is 1.5 amps times 6.75 for 6.75 for the first bulb, and 1.5 times 6.75 gives you approximately 10.1 watts. For P2 for bulbs 2, 3, and 4, it's going to be equal to 0.5 amps times 2.25 volts, and that's going to be equal to 1.12 watts approximately. And so the brightest bulb is the one with the most power, and so that's going to be bulb 1 here because it has the most power going through. All right, that wasn't too bad. Moving on to question number 7 here, which is a Kirchhoff's law problem. So we're starting with find the current in the 3 ohm resistor. We can use Kirchhoff's junction rule for this. So this is 3 amps going up this way. This is 5 amps going up this way. And so we see there's a junction here where there's 3 amps going in, 5 amps going in. And so the output should just be 3 plus 5, which is 8 amps. That verifies the junction rule that agrees with the junction rule. And so it has to be 8 amps through the resistor 3. Or not resistor 3, the 3 ohm resistor, because they didn't label it, unfortunately. Find the unknown EMFs, EMF 1 and EMF 2. So we can use Kirchhoff's loop rule for that. So let's start by assigning this to be a loop and assigning this to be a loop. They are going in opposite directions, and that's fine. They can always go in opposite direction. It's just whatever's nicer. In this case, we're going whichever way the current is going. And so let's start up here. First, it goes through 4 ohm resistor, and so it's negative I times R, which is negative 4 times 3 or negative 12 volts. Then it goes up through this resistor, also in the same direction that the current goes, which would also make it negative. This time it's negative 3 ohms times 8 amps. That's how many current is going through it. So it's 24 volts. And then plus this EMF 1 is equal to 0. And so we just move everything to one side and we get EMF 1 is equal to 36 volts. So this is a very simple example of Kirchhoff's loop rule. There are much more complicated examples out there, but I would suggest doing some worksheets or textbook problems based on that. If we do the same thing to the other side, we get, if we start up here and go down, 6 times 5 is 30 volts. Then 3 times 8 again is 24 volts, plus epsilon 1 is equal to 0. And so moving everything to one side, we get 30 plus 24 is 54 volts for EMF, sorry, this is EMF 2. EMF 2 is 54 volts. So that's our answers to part B. And our answer to part C, the resistance R, is up here. We can use another loop. Let's just go this way because that's the way the current is going and start up here. We're going along with the current through the resistor. So that's negative I times R. I is 2, R is R. So negative 2R. R is the variable here. Then we're going through the EMF from the positive to the negative. So the positive to the negative means we're actually going the opposite way, which means it'll be negative 36 volts, because that's the EMF of EMF 1, and we're going the opposite way, so it's negative. We're going negative to positive in EMF 2, so that's going to be plus 54 volts is equal to 0. And so 54 minus 36 is 18. And so negative 2R, negative 2R plus 18 volts is equal to 0, which means 2R is equal to 18 volts, or R is equal to ohms. 18 volts, but since 2 is in amps, it's volts per amp, which is ohms. So R is equal to 9 ohms. So yeah, that was a pretty easy example of Kirchhoff's laws. So I would suggest doing more practice on Kirchhoff's laws because you can get some ugly problems that require you to do systems of equations to find the resistances. Okay, this last question of ours, almost done with the video, is an RC circuit problem. And so this question is saying we have a capacitor, we have a resistor, and we have a battery with 10 volts. What is the current when the capacitor has acquired 1/4 of its maximum charge? Okay, so the equation for current is Q of t is equal to Q maximum, which is just C times V, or C times epsilon. Depends on if it's a voltage or EMF. The reason why we know this is because from last unit, we know Q is equal to CV. And so we plug that in here. Times 1 minus e to the power of negative t over RC. And so we can plug in stuff. We know C is 1.5 microfarads. We have to convert that into farads. This is 10 volts. We know T is what we're looking for, actually. R is 12 ohms, and C is 1.5 microfarads again. And this is 1/4 of its maximum charge. What did we say what Qmax was? C times V. And so you can actually divide both sides by C times V. And we're just going to get 1/4 is equal to 1 minus e to the power of negative T over RC. And so we're solving for T here. But we actually don't have to. It seems like we have to solve for T because most problems would ask us to find the time at which you have acquired 1/4 of its maximum charge. But we can do something a little sneaky here. And first talk about current. Current is equal to the maximum current, which is V equals IR, so V over R, so EMF over R, or V over R, times e to the power of negative T over RC. So the maximum, so in this case, we can't divide by anything because we're looking for the actual current, not the fraction of the current. And so V is 10 volts, R is 12 ohms. And what is this term? Instead of solving for T, we can actually solve for this entire term from this equation. We just have to subtract 1 from both sides, giving us negative 3/4 is equal to negative e to the negative T over RC. So taking the negative sides off, we get 3/4 is equal to e to the negative T over RC, which means this term is equal to 3/4. And so I of T is just 3/4 of 10 volts over 12 ohms. 10 over 12 is 5 over 6. And so I of T is equal to 0.625 amps. So this is when it's the 1/4 of the maximum charge. And will it be 1/4 of the maximum current? No, it will not. We just proved it's 3/4 of the maximum current because this right here is an expression that determines the maximum current. We just said it was 3/4. And the reason why is because the equation is different. This is 1 minus an E term. This is just an E term. And so that's why it's 1/4 versus 3/4. It's 1 minus each other. And yeah, that was it for Unit 3, which is current, resistors, and circuits. And I'll see you in the next unit, which is the start of magnetism, which is very fun. So yeah, I'll see you there.